Good morning. Thank you for joining us for our STS-119 mission overview briefings. Joining us today are Lead Space Shuttle Flight Director Paul Dye and Lead Space Station Flight Controller Quetzalcoatl Barahu. We'll start with opening remarks from both and then take questions from the Johnson Space Center and other participating centers. We'll start with Paul.
Okay, thank you. Well, it's great to be back talking about a new mission in the new year. It's amazing after the holiday that we're hitting the ground running and getting ready to go right off the bat. We just had our last full-up integrated orbit sim the other day with the crew and my whole team and Quetsy's team, and everybody's hitting on all cylinders. We're getting ready to go. It's very exciting. If I could have the first slide, we'll talk a little bit about what we're going to do the mission. Of course, we always start off with a picture of our crew. This is a kind of a fun crew for me because we do a lot of generic training. Not only flight-specific training, but a lot of simulations all the time. We're always busy training new flight controllers and crew members. And this particular group of guys are names that I see all the time when we've been doing generic training. And so I've worked an awful lot with the whole group. I'm going to let them introduce themselves in the afternoon briefings or later this morning, and we'll talk about them then. But Brew and Tony and Swanee and Ricky Arnold, Joe and John. And they're all great guys. We've worked with them quite a bit, and I'm really looking forward to having them on all on orbit for us. The STS-119 mission is something I came to after a lot of the work had already been done by Quatsy because of a reassignment, and I'm really excited to be part of this because you take a look at the space station, and I've watched it grow from the very first mission 10 years ago, a little over 10 years ago. And to finally expect that we're going to see it as we back away with all the solar arrays complete and all the truss structure built out is just amazing. When we got started on this, it was a dream, and it was some really neat pictures, and it was a lot of hardware sitting down at the Cape, and now that hardware is sitting on orbit, and it's actually working, and that's really going to be exciting. We're going to have a number of folks working the shuttle flight director side of the console. We've got a few pictures of them. If we could see the next slide. Mike Serafin was the lead flight director on the last flight. He's coming back to work the Orbit 2. That'll be the crew afternoons. I will, of course, be working Orbit 1, which will be the crew mornings, which I think are some fairly early morning hours here in Houston. Mike's got about 5 flights now in the shuttle flight director role. Very, very solid player. Next slide. Norm Knight, who's our lead ascent entry guy, normally is going to be working half the flight on our planning shift for us, and he'll be sharing that with the next slide is Brian Lunny, our second-generation flight director. I think Brian's going to be working the first half of the mission on the planning shift, and Norm will be working the second half. Both those guys have about 6 flights worth of shuttle experience, which is quite a bit. Next slide is Tony Sakachi. He's going to be working our Team 4 activities, if we have any, and he'll also be subbing on some of the shifts to make sure that folks get a little bit of a break on a very long mission like this. And lastly, we've got a picture of Richard Jones, who's going to be flying the ascent and the entry. He'll be coming in, doing the ascent, and then coming back again for the day before landing, and then flying the entry for us. And Richard has about 5 flights of experience. Take a look at the payload bay, what it's going to look like here. We've got a little video, I think. Go ahead and play that. I like this kind of mission. We've got one great big payload in the payload bay. That's the truss segment. We also, as normal, have the orbiter docking system up in the front. It's basically a permanent fixture. The shuttle RMS, it will be on the port sill as always, ready to go. And then on the starboard sill, we have the orbiter boom sensor system, which we use for our inspections. And the S6 truss basically fills the bay. Talk a little bit about the mission activities. Flight day 1, of course, is very standard. We'll have the ascent. Hopefully we'll get some good weather. We'll be doing the ascent imagery. We'll take a good look at the entire vehicle on the way uphill. We'll get all that data down as quickly as we can, and before the crew goes to bed, they'll hopefully unlimber the arm and do RMS checkout. Flight day 2 has gotten to be fairly standard as well. That'll be the day that we do all of our post-ascent TPS inspection. We have video of that. Bring the arm out, our arm, and we go over and grapple the orbiter boom sensor system, the OBSS, which gives us the extra reach that we need in order to inspect all areas of the vehicle. And then we go out and we start scanning. And hopefully we won't scan this fast. We would love to do the inspection this quickly, but this just gives you an idea of how the arm moves, but considerably slower than that. And we'll take a look at all the RCC. We'll take a look at sides, underside of the payload bay, doors, and upper wing surface on the starboard side. Then we'll go ahead and swing around, do the nose cap, the high temperature nose cap, taking a look at that whole area. We get all this imagery, and all this imagery comes down, and then we have an army of folks in the mission evaluation room who will spend about 2 days looking at every little teensy-weensy bit of footage, make sure we don't have any problems or any difficulty of any kind. And if anybody ever moves the arm that fast, I'll be surprised. Okay, so once we finish that up, we'll also be doing, on that day, we'll be doing the EMU checkouts, making sure that the spacesuits are ready to go. We'll be doing the centerline camera installation. We'll be extending the docking ring. We've got, of course, rendezvous ohms burns to phase us towards the target, and going ahead and getting ready for rendezvous on flight day 3. Flight day 3 rendezvous is going to look very much like usual. We have the some more animation of that. If you want to bring that up. We're going to be going on up to about 190 plus nautical miles, and we will be doing a rotational pitch maneuver. Do we have that video? There we come. We'll be approaching from behind and underneath, coming up the as we call it, the R bar, the radius vector. And we'll get down to about 600 feet, or get up to about 600 feet. We'll be doing the pitch around, the rotational pitch maneuver to allow the crew on board the space station to image us, to take a lot of pictures with a 400mm lens and an 800mm lens. They'll be looking at all the surfaces of the orbiter. But I think these are some of the most spectacular pictures I have seen in the entire history of the shuttle program, is the pictures we get during the RPM, to see the Earth rotating underneath the orbiter as the orbiter basically does a loop in one spot. It's again amazing. We'll get all of this data down. We'll send it over to the mission evaluation room, and the group of imagery experts will take a look, and they'll look at every square inch of the vehicle, making sure that we are in good shape. If we have any issues at all, we can go ahead and do a focused inspection on another day to tell us whether we have any issues or problems. But so far, we've been looking amazingly well after all of the inspections. Once we finish the rotational pitch maneuver, we'll go ahead and transition using what we call the Torva maneuver, which brings us up to the V-bar, which is a fancy way of saying that we're directly out in front of the space station with our bay towards the station. And then we'll back in slowly along that velocity vector to a nice clean docking. Basically, it's a continuous series of little hops on the V-bar. We come into about 30 feet, we stop, we do an alignment check to make sure that we're in the same relative orientation as the station, take out these little 1/2 to 1 degree errors, and then we'll go ahead and continue on in for the hard mate. Okay. Once we get in and hard mated, get all the latches closed, the crews will open the hatches. We'll do the IELK transfer right off the bat. We'll set a few things up. And then the hard part of the mission for me is almost done, because at that point I turn the stick over to Mr. Alabarujo on the station side, and he's going to go ahead and tell you about all the really exciting things we're going to do on this mission.
Good morning. As Paul said, it's a pleasure to be preparing for another exciting space station assembly mission. This will be my first lead assignment. I was assigned to this mission about 1.5 years ago, and the entire team that's been working on this flight, as well as the crew, has done an absolutely fantastic job, and we are very much looking forward to seeing the space station appearing to the naked eye as it has appeared for so many years in drawings and in schematics, and basically seeing the integrated truss segment complete is going to be really exciting. For this mission, as on the shuttle side, we'll have several folks supporting us. If we can see the next slide. Our Orbit 2 flight director, again, who will be working on the crew afternoons for the space station team, is Miss Heather Rarick. She's got considerable experience. She formerly was a Russian operations lead for the Houston Support Group, our liaison team in Moscow, and has a considerable amount of experience in leadership of space station operations. She was most recently the lead station flight director for Expedition 17, so we're very excited to have her working the Orbit 2 shift for the space station team. And next slide. And then one of our newer flight directors, Mr. Dave Korth, also a very experienced individual, formerly an operations planner. He will be working the planning shift, the Orbit 3 shift for station side, making sure that the crew and the ground teams have good plans to execute each day. Again, very much looking forward to working with him. He's an exceptionally talented individual and will do very well. Next slide, please. For any contingency operations that require some integration off console, Dr. Bob Dempsey will be our Team 4 station flight director, and with the complement of flight directors that we have for this mission, we are expecting to have a great mission. We're expecting to be able to deal with any issues that arise in an expedient manner, and very much looking forward to working with everyone on this operation. Just tell you a little bit about the S6 truss segment, which is a primary payload. It's an extraordinary piece of engineering. It is the last integrated truss segment that will be installed on the ISS. It will provide additional power for the space station that will be used for core systems operations, as well as for additional payload that we will have in the international partner modules now that we've successfully installed the JAXA module as well as the ESA module. We have a video of the S6. If we could show that at this time, we'll go into some detail about the capabilities of the segment. Very much like its sister segment, the P6, it's on the end of the starboard side of the integrated truss segment. You see there the beta gimbal assemblies. They will be rotated out following EVA 1, which is where the truss will be installed. There you see the solar array blanket boxes that houses the folding solar arrays that will be deployed on flight day 8. Integrated into the truss, on one side of it, you see the photovoltaic radiator that provides cooling for the batteries and other electrical components when they're under load. Anyone that's ever had rechargeable batteries in their home knows that they get hot when charged and when discharged, so the photovoltaic radiators provide cooling capability. As was the case on previous solar array deployments, the S6 solar arrays will be deployed in a staged manner, which we'll talk about in more detail later, but we'll deploy them one at a time, and once they are fully deployed, they will be able to provide electrical power to the rest of the space station almost immediately, as well as provide power to charge the battery units. Other interesting items about the S6 truss segment. It's about 16 feet wide, 45 feet long. It weighs about 31,000 pounds. It's actually one of the lighter truss segments that we've flown for that has photovoltaic modules on board. The architecture consists of about 12 batteries, 6 battery charge and discharge units, 2 primary switching units that allow you to apply the DC power to the rest of the station once the solar arrays are getting good sunlight, and the whole truss segment is controlled by two computers, redundant computers that provide command and control for the switches, the battery charging, as well as solar array pointing. Just to give you an idea of the power generation capabilities of the S6 truss, each solar array can generate about 33 kilowatts of power. The entire truss segment itself generates about 66 kilowatts of power. Just to give you an idea of what that means, that's enough power to power approximately 32,000 square foot homes. So once the S6 is installed on the space station, the entire space station's power generation capability, at least from the U.S. Provided hardware, will be right around 264 kilowatts. So it's very impressive, and we're excited about having that much power available again to support not only core space station systems operations, but all of the science that's going to be performed not only by our partners here in the U.S. At Marshall Space Flight Center and around the country, but also scientists in Japan and in various portions of Europe supporting the European Space Agency. We're very excited about that. Just to talk a little bit more about the sequence of events for the mission and how we'll carry out the installation of the S6 truss. We'll start on flight day 4. As Mr. Dye has indicated, when the shuttle arrives, the S6 will be in the payload bay. If we can show an animation of the S6 unberth, we'll describe that in more detail for you. One of the things that's unique about the robotic operations on this mission, as you can see there, with the presence of the JAXA module now on the space station, the shuttle robotic arm does not have sufficient clearance to unberth the S6 truss from the shuttle payload bay. The station robotic arm will be used to do that. However, the station robotic arm will then hand the truss to the shuttle robotic arm, where it will then prepare to translate further outboard on the starboard side of the truss, where it will then take the truss back from the shuttle arm and then maneuver the S6 truss into a position where it can then be installed. What you're seeing there in the animation that's going fairly expediently will actually take most of flight day 4. In fact, this is the crew's primary objective on flight day 4. That's the day after the rendezvous of the shuttle and the docking. And essentially, flight day 4 will end successfully with the S6 truss segment in what we call the overnight park position, and that's a special orientation that has been analyzed thoroughly, such that we know that the truss, which will still be unpowered at the time, will be in a good shape for its temperatures that won't get too cold, as well as since you'll have a large mass of metal in an asymmetric configuration there, we also have to consider the ability to control the International Space Station and the shuttle stack with our control moment gyros. So the position that we're going to park the truss in overnight was specially selected to be optimal for thermal as well as for controllability. That brings us to flight day 5, which is where the fun continues. That's going to be the day where we'll execute EVA-1, which will be the installation of the truss. If you could show the next still picture, please. Spacewalkers for EVA-1, the S6 installation will be EVA crew member Steve Swanson, who's a very experienced EVA crew member. He'll be the lead EVA crew member on this mission, and he'll be assisted by Spacewalker Ricky Arnold. Our lead EVA officer, Glenda Brown, will be here to brief you later today on more of the details of the EVAs. If we could show the video of the S6 install, we'll give you a better feel for what's going to have to happen with the truss to get it installed. As I said, at the end of flight day 4, the truss will be in an overnight park position. What you're seeing there now is the robotic arm on the morning of flight day 5 maneuvering the truss from its overnight park position to the installation position. The truss will then be soft mated to the S5 integrated truss segment. At that point, the EVA crew members Swanson and Arnold will translate to the end of the truss, where they will manually bolt the S6 truss segment to the S5 truss segment using the Rocketdyne truss attachment system. It's a manual bolting system, unlike the bolting system that was used to install S4, and that system that installed S4 was motorized. But for the outboard truss segment, it's manual. They will use their EVA power tool to manually drive the bolts and connect the S6 to S5. Once the S6 activation is complete, the activation will be carried out mostly from the ground after the EVA crew members have installed the umbilicals. Once they've installed the electrical and power and thermal connections required to support S6 activation, flight controllers here in Houston in the Space Station Flight Control Room will actually be executing the rest of the initial activation of the truss, which will include starting up the computers and starting up the cooling system. Once the S6 has been activated, we then have to position the robotic arm to support focused inspection on flight day 6 if it ends up being required. That will require the mobile transporter to translate to worksite 4. If you could show the next video, video number 5. So essentially, the robotic arm has to make a trek further inboard, so that again the station robotic manipulator can unberth the orbiter boom sensor system and then hand the boom to the shuttle arm to carry out the focused inspection on flight day 6. Now, as Paul indicated, we've seen very good performance from the tanks with respect to debris shedding over the last several missions, and the last few missions focused inspection has not been required. So if we continue to have good fortune on this mission and the focused inspection is not required, some of the activities that normally would have fallen later in the mission, particularly the solar array deploy, will be moved forward into flight day 6. But for the case where focused inspection is required on flight day 6, we will execute that. There will be a walk-off of the station arm from the mobile transporter system to the Node 2 to support that, and then we will then have to translate the mobile transporter system back to worksite 1, which is where we installed the S6 truss segment to support our operations for the subsequent day. On flight day 7, EVA-2 will be carried out by spacewalkers Steve Swanson once again, and this time Joe Acaba. If we can show the next slide. And for EVA-2, the primary objectives will be the replacement, or I should say preparation for the replacement of some batteries on P6. As you may be aware, the P6 truss segment, which was the first photovoltaic system that was delivered to the ISS several years ago, the batteries on that system are due for replacement. They're going to be replaced on the following mission. Right now, they're planned to be replaced on STS-127. That's ISS-2JA. So in order to prepare for that replacement, we'll be doing some reconfiguration of the batteries on the P6. Also, we'll be deploying an external payload attachment system on the Port 3 truss segment, as well as doing some other get-ahead tasks on the port side for EVA-2. And just to give you a feel for where those batteries are, again on the Port 6, if we can show the next slide. There you see in the center of the view the suite of batteries that will be replaced on the mission following this one. Will essentially be going out to the port side and breaking the torque on the battery housings and setting them to a torque that we feel will be able to be more quickly addressed when the batteries are actually replaced on the following mission. That brings us to flight day 8, where for the nominal timeline, we'll continue to configure the S6 truss segment for its final configuration to be able to receive power from the sun. That will be solar array wing deploy. This will also be a highly choreographed operation where we will deploy the solar arrays on S6 sequentially. If we can see the animation of that, we'll give you a feel for how that's going to occur. As you can see there, the beta gimbal assembly housing rotated into place in preparation for the deploy. We'll do that on the channel 3B array, which is the one that will be facing forward toward the orbiter, and the channel 1B array, which will be facing aft toward the Russian segment. The timing of the solar array deploy has to be precise because we depend very heavily on lighting front conditions from the sun to let us know that the mechanism is deploying properly. As we've seen on previous flights, this is an outstanding deployment mechanism. It's a very complex mechanism. When everything is working well, it goes very smoothly, but sometimes there may be potential for issues. The most notable issue that we've seen during deployment is stiction phenomenon. Basically, the solar arrays consist of they're coated with polymers and other chemicals, which, when their arrays are packed in their blanket boxes, sometimes can stick together. The stiction problem is alleviated with thermal conditioning, so we will deploy each array about halfway. There you see the 1B array being deployed, and now the 3B array, which is the one facing forward toward the orbiter. We'll deploy it halfway and then wait for about a half an orbit for thermal conditioning. The sun will sort of warm these polymers that we talked about and allow them to unstick and allow those folding solar array panels to release, and then we'll complete the deploy. And there at the end of that, as you see, the S6 will now be able to generate power on its own and pass that power to not only its own battery assemblies, but also to other loads on the station. Following the solar array deploy, we have yet another MT translation to worksite 4, and this is to get the station arm to the position that it needs to be in to support viewing for EVA 3. Later on in the day, the crew will be doing preparation for EVA 3, which includes their procedure review, as well as conducting EVA preparation, the camp-out operations, which is essentially where we put the spacewalkers in the airlock overnight to help purge the nitrogen from their blood so that they can support the spacewalk the following day. In preparation for this mission, there was a considerable amount of engineering analysis that was done prior to the previous mission and ongoing analysis to determine how the solar array rotary joint will be able to support the rotational loads with the new S6 truss segment on it. You may recall from the previous mission, one of the key objectives was to lubricate and clean the starboard sarge, which we had seen some issues with. Evaluation of that mechanism following the last mission shows that the cleaning operation and the lubrication that was performed has helped the health of the mechanism considerably, and we have high confidence that the solar array joint will be able to function properly with the additional mass of the S6 truss segment on it. So after we successfully deploy the arrays on Flight Day 8, we expect the integrated system to be in good shape and functioning nominally, tracking the sun. Flight Day 9 is when we'll execute the third of 4 EVAs on the mission. Spacewalkers for this mission, for that EVA, will be Ricky Arnold and Joe Akaba. If we could show them, please. The primary objectives for EVA 3 will be to relocate one of the crew equipment translation aids, CETA carts as we've come to know them. Also, we'll be replacing 2 power switching units that are on the truss. These are units which experienced some failures some time ago. They're still passing power and still providing power to the loads that are required. However, we do have indications of some health issues with those boxes, and we want to replace those power switching units before a significant problem arises, so that they can be refurbished on the ground and reflown later. So one of the big ticket items on EVA 3 will be to replace those power boxes. Replacing those power boxes, of course, requires unpowering a considerable number of loads that are supported by the upstream power distribution unit. That's done to provide safety inhibits for the EVA crew members as they're mating and demating power connections. So while the operations on the spacewalk will look fairly benign to the casual observer, in mission control while this operation is underway, there'll be a considerable amount of ground commanding, reconfiguring the thermal control system, reconfiguring the communication systems, and reconfiguring other payload systems that might be affected by the temporary power outage. Also, we'll be completing some reconfiguration of thermal covers on the special purpose dexterous manipulator, the SPDM, and we'll be performing lubrication of the Lee B on the space station arm. Again, on the previous mission, this task was first performed for the other side of that arm, and we saw good results from that. So we're going to be lubricating the Bravo side of the space station robotic manipulator, and again, that's done as more of a preventative maintenance item. Flight day 10 will be a half-off duty day. By the time we get to flight day 10, our crew will have performed a number of activities and definitely be in need of some well-deserved rest. They'll be participating in news conferences as well as doing some basic preparation for the fourth and final EVA, which will occur on flight day 11. On flight day 11, we will do EVA 4. Once again, we'll have spacewalkers Steve Swanson and Ricky Arnold, if we could show still number 11 with their pictures. And the main objectives for this EVA will be the installation of a GEM GPS antenna that will support proximity operations for the H-2 transfer vehicle. That's the Japanese logistics vehicle that will fly later this year. And we'll also be performing some other reconfigurations and get-aheads. One of the more significant operations that we'll be performing on EVA 4 will be infrared imaging of the port and starboard radiator beams. You may have heard that there is a torn blanket on one of the radiator surfaces, if we could show that picture. Flight controllers noticed this torn blanket on one of the radiators some months ago. There's still an investigation ongoing within the engineering community to try to identify root cause. But the infrared and standard imaging that will be done on this mission of all of the radiators will be targeted at seeing if there is any degradation in the performance of the thermal control system as a result of the damage to that radiator. As yet, there has been no noticeable degradation in performance with respect to the capability of the integrated system to reject heat and support all of the nominal planned loads. But the infrared imaging of the radiator will give us a very good feel for how the damaged radiator is radiating heat from the loads it's supporting, and we'll be able to compare that against the imaging that we get from a healthy radiator. So that's why we're going to do the IR imaging of all of them. We'll then move back to the Z1 truss, which is at the top of the Node 1 Unity module, and reconfigure some electrical patch panels that are there. And then we'll install a wireless EVA antenna assembly to augment our capability to get video from EV crew members' helmets while they are outside. The EVA will finish up with deployment of another 2 external payload attach facilities. Again, we are very much looking forward to all of the science that we'll end up doing on the space station. So one of the things that we're excited about being able to do on this mission is reconfigure some of the mechanical interfaces that are required to support that science in the future, and that will wind up finishing out EVA 4. So that's a summary of the major activities that will be occurring during the docked phase. At this point, we'll turn the briefing back to Mr. Dye, who will talk about what the shuttle will be doing as it prepares for departure and afterward.
Okay, thanks, Kwatsi. That's an awful lot to accomplish in a short period of time. It's going to really change the face of the station, and it's going to make it look pretty spectacular, which of course is something we're going to look at when we undock. Flight day 12 is very typical. It's the day when all EVAs are done, all the assemblies done. We'll be going ahead and making sure that we have everything put away the way we want it, get all the EVA suits back where they're supposed to be. We'll go ahead and make sure that the crew member exchange is complete and that everybody's ready to come home the way they're supposed to be. The Discovery crew is going to have about a half day off duty which will be nice after all that work. And then, of course, at the very end of flight day 12, we'll go ahead and they'll be doing their hatch closure and farewell so that they're ready to go for undock the next morning. Flight day 13, we start with the undock. So if you give me video number 4. Typical undock, we'll back out to around 600 feet. And then we'll do the fly around of the station to get some photographs of what it's going to look like with all the solar arrays deployed. So it'll be a typical 1 rev plus a quarter fly around. Again, don't expect it to go that fast. We just speed it up for animation, and then when we get back on the top on the outer R bar, we'll go ahead and do a SEP burn and leave the vicinity of the station. Of course, once we've been in space for that long, we're worried about any potential micrometeorite impacts that could have occurred to the station. And we're going to have to go ahead and inspect for that. So if you give us video 5, it's going to look a lot like what we do at the beginning of the mission. We go ahead and we take a look at everything. Now, on about flight day 5, we would have cleared the vehicle for entry based on ascent debris. This inspection is to make sure that we are cleared from a micrometeorite and orbital debris impact potential. So we'll look at everything, look for any other impacts on the leading edges of the wings, on the nose cap, and make sure that everything's in good shape from that respect. If you remember, on several of the past missions, this is a period of time when we seem to see little things coming off the vehicle, actually during FCS checkout the day after. We're very, very cognizant of that, and we've now given the crews additional training to be looking out the windows with a camera to capture anything that might float away. Because it's almost always some very, very tiny object which is loose and won't have any impact to the vehicle whatsoever. And if we make sure that the crew is looking, that gives us the opportunity to dismiss those things correctly and very quickly. So flight day 14, cabin stow, FCS checkout, RCS hot fire, making sure that the jets are all up and ready to go. Basically, it's all the things you need to do before you're ready to turn this thing back into an airplane and come on home and land. Flight day 15, of course, is the deorbit prep and landing, and hopefully we'll be back on the ground. We do have, as usual, a couple of weather extension days in our hip pocket in case we don't have the kind of weather we want for landing. All in all, this is going to be a pretty exciting mission, and I'm really looking forward to getting these vehicles and this crew back in space to finish up the truss segments on the space station.
All right, thank you so much, Paul and Quatsi. We'll now take questions here from the Johnson Space Center. If you'll please identify if you're interested in a question, and please state your name and affiliation.
My name is Taku Tsuchiya from Nippon TV. This is a Japanese TV station. Could you tell us more about Mr. Wakata is going to do during the 2 weeks period, specifically?
Absolutely. One of the primary objectives of this mission is crew rotation, which has become fairly standard for space station missions. We will carry JAXA astronaut Koichi Wakata up to the space station and return astronaut Sandy Magnus down on the shuttle. While on orbit, Mr. Wakata will be heavily engaged in the robotic operations that we described, as well as doing some experiments for principal engineers and investigators affiliated with JAXA. Mr. Wakata will be supporting the S6 unberth operations and maneuver on flight day 4. He will also be heavily involved in the robotic operations with John Phillips on flight day 5, where we install the integrated truss segment. We're very, very fortunate to have the benefit of Mr. Wakata's robotics expertise. He's become almost legendary among the astronaut corps for his ability to operate the space station robotic system. And given how complex the robotics are on this flight, it's very fortunate that we have the benefit of his expertise. There are also a few payload operations during science briefing at some time later. That will be discussed in more detail, but there are experiments, rad gene, dome gene, and some other experiments which are being flown up on the orbiter for transfer to the space station. Mr. Wakata will be the principal crew member that will be involved in carrying out that experiment and reporting the data to the engineers on the ground in Japan.
Okay.
Yeah, Jim Overg with NBC. Paul, you mentioned this interesting additional work to characterize objects outside the window. These things tend to come off. How often do you see things floating by, and what are some examples of some of the source of these kind of objects?
Good question, Jim. As we've noticed during STS checkout, when you start up the APU and you wiggle the elevons around, it's not uncommon to shake loose a little bit of ice. They can come off the engines. We've had very small pieces of T-seal come off, things like that. Not T-seal, a little bit of seal that comes off from between the rudder and speed brake. I forget the names of those actually. We've not had anything significant, and that's the point. It's not uncommon to shake a nut or a bolt or a washer that was left in the payload bay by accident out. Nothing that we're going to miss, but when you see it and you just glance at it, you can't tell the range. So what we've trained the crew to do is to get a couple cameras on it so we can triangulate on it real quickly, and then we'll know its size and its range and where it's going, and we can very quickly say, we know what that is. Good example was the little seal that came out between the rudder speed brake a couple flights ago, I think it was, and the folks, once we got a camera on it, the crew was the guys on the ground looked at it very quickly and said, we know what that is. It's no big deal. It's just there for ascent. Don't worry about it.
The big piece that they didn't see but might have was on Columbia, wasn't it? On flight day 2 when the hunk of the RCC came loose. So
that was before we were doing all these inspections.
Exactly. Right. So
we could see, and that's why we do this, is to make sure that if there is something significant, we'll know that as well.
It's about time. Thank you. Also, it's a good press coverage because the internet gets a lot of interest in those little things floating by the window. No comment. Thank you.
Any remaining questions here at Johnson Space Center? Okay, with that, we'll move on to Kennedy Space Center, where we have a reporter.
This is Marcia Dunn of the Associated Press. First for Paul, do you have any extra days you plan to insert during the flight in case you get backed up on space station work?
Well, we always have some cryo in our hip pocket, and we're always looking at how we can grow that. One of the interesting things for me is that early on in my career, our estimation techniques for how much cryo we were going to be using were not as refined as they are today. So you could almost always count on growing your cryogenics, growing the margins as the mission went on, because we were always conservative in our estimates. Nowadays, our analysts have gotten so good and so precise that they don't keep as much margin because they're very, very confident what they're going to get. So we don't see that growth quite as much. But as always, if we need an extra day and we build some extra time, we'll see if we'll use what we need to use and what we have capability-wise. I'm not sure what we're going to have on our liftoff numbers. Of course, we won't know that until we actually get into the cryo load, and then when we get off the pad, we'll determine about how much extra we carry.
And another question for you. You're going to have 2 former teachers on board this time together. Are there any kind of educational events planned, and has there been anything about having 2 teachers on board that has set this apart in your estimation?
It's kind of an interesting question, because I don't really think of these guys as teachers as much as I think of them as fully qualified spacewalking space station assemblers. Yep, both of the guys came out of both Ricky and Joe came out of the educational program, and we don't have any particular educational activities planned at this time for either of them, because they are out there to do the assembly job. So it really isn't something that crosses my mind. They've melded into the astronaut corps like everybody else, and they can do exceptional, exciting work.
Thank you. And one question for Quatsi. The last time a solar panel was unfurled, it ripped. And is there anything from that event that you're going to do this time to avoid a repeat?
Marcia, I'm glad you asked that. We have spent a considerable amount of time analyzing the circumstances that led to the damage to one of the solar arrays on P6. In fact, we have a picture of that, if we could show that, please. While we were redeploying the solar arrays from the P6 truss segment during STS-120, that was the ISS-10A mission, they had been repacked on the previous flight, 12A.1, in preparation for the P6 relocation. And essentially what our investigation revealed is that during the EVA efforts to repack that solar array, one may recall the EV crew members had to intervene with the mechanism considerably to get the solar array to retract and to get it packed in its blanket box again to prepare the P6 truss segment from relocation from its temporary home, which was on the Zenith truss, over to the end of the port side truss. During the interventions to repack that solar array, one of the guide wires in the mechanism became fouled. It was really a situation that could not necessarily have been foreseen or avoided. EV crew members have to be very, very careful when interacting with the solar arrays. Solar arrays of this size are not something that an EVA crew member can just reach up and easily touch with their bare hands and gingerly pack in the way we might pack a blanket in our homes, because these solar arrays generate an incredible amount of power. And even when you don't have the solar arrays connected to a downstream power switching unit, just the voltage potential, the electrical potential generated could be extremely hazardous to a crew member if an EVA crew member, even with their gloves, were to touch them directly. So as we were packing the blanket box on the P6 truss using an extender tool, a non-conductive extender tool, one of the guide wires in the mechanism essentially got fouled, so that when we redeployed that solar array on the last truss install flight, which was on STS-120, we also basically had a bit of bad luck with respect to lighting, because at the precise moment when that guide wire basically snared itself on the solar array blanket, there was what we call a sun flare. Essentially, the position of the sun relative to the solar array essentially caused the light to shine in the cameras, and it temporarily obscured the crew member's view of the various pieces of that mechanism during the travel. So what we've done for this mission, first off, we don't expect to have a similar problem, because the solar arrays that will be deployed were packed and configured on the ground by engineers. So we have high confidence that there are no issues or misalignments or any otherwise congenital problems with the truss. And we've structured the solar array deploy operations on flight day 8 such that lighting conditions should be optimal for all of the crew members on board to see every critical part of that mechanism as it's deployed. The method that we use for alleviating stiction, again, which is a partial deploy of the solar array, we pause at about 49–50% deployment for thermal conditioning. Not only do we get the thermal conditioning benefit, but it also gives us time to do a thorough inspection of the solar array mechanism, do an inspection of the tension mechanism. There's a mechanism on the drive unit that indicates tension. Inspect the wires and all of the key portions of the mechanism before we drive the extender further beyond the 50% point to the point where we apply tension. The staged method that we're using on this flight for deploying the solar arrays was not used during the operations to deploy the P6 solar array last time. The reason it was not was because the primary driver for us to use this stage method, of course, was the stiction phenomenon. Since the P6 solar array had already been on orbit for several years, stiction was absolutely not expected to be a problem. And the additional problems we had with the mechanism for the P6 solar array basically served as an excellent lesson learned for us. And so now we have a method that we have high confidence in as far as being able to deploy the arrays without an issue. So we think that the factors leading to that event on the last solar array deploy, we're not expecting them to be an issue this time because we have addressed it. Great question, though. Thank you.
Thank you, Kwatsi. We'll now turn to our headquarters office in Washington, D.C. for media questions there.
Thank you. This is Tariq Malik from Space.com and Space News, and my first question I think is for Quatsi or Paul. I was just curious what the impact of the addition of the UPA for this flight, the spare part on the shuttle means that you have to give up for maybe extra payload for the station, Quatsi, and maybe how that troubleshooting impacts your work during the flight.
Okay, that's a great question, Tarek. We've done a preliminary assessment of the impact of having to fly up the urine processor distillation assembly. Just to provide some background for the viewers, currently on orbit, we're experiencing some problems with the ISS urine processor distillation assembly. You might have heard Program Manager Mike Seferdini describing some of those concerns in detail. But essentially, the space station program is looking at flying up a replacement unit on this mission. The final decision on that hasn't been made. We're waiting for the results of some additional on-orbit troubleshooting that will be conducted on the incumbent distillation assembly. It is a fairly large and weighty unit. We have done an assessment of our capability to carry that up on the orbiter middeck. It has to fly on the middeck since the P6 truss segment is taking up all of the room in the payload bay. A preliminary assessment suggests that basically some logistics support equipment might be displaced. These are things that won't have a significant impact on science, so we will not be potentially displacing payloads, basically just rephasing some of our logistics support equipment. And once the spare distillation assembly is on orbit, if we have need to fly it, we do have ISS Commander Mike Fink and incumbent Flight Engineer 2 Sandy Magnus. They have been thoroughly trained in how to remove the off-nominal distillation assembly and install the new one. So the good news is we've had enough of a heads up to take a look at that. Final decision on that has not been made. Final decision on flying the distillation assembly has not been made. Final decision on replacing it hasn't been made. And just given the nature of the business, we won't have enough data to make that decision until probably a few weeks from now. But our crew is ready to support that. Our incumbent station crew is ready to support that replacement. And we have turned on the engineers that are supporting configuration of the orbiter to be able to pack the distillation assembly on the middeck and return the failed distillation assembly back if required.
Thank you. And my follow-up would be for both Quatsi and for Paul. This is the last of the big solar wings to fly, and given that you've had practice with the last three, I'm just curious what, I guess, does this particular activity seem a little bit maybe more routine than now, or where would you see kind of the hump of the flight where you can kind of breathe a little sigh of relief to say, whew, it's downhill from here? Thanks.
That's a great question. One thing I'll say at the start is that spaceflight is never routine. You've heard me say in previous press briefings something that I believe very strongly, and that is that the International Space Station program is extraordinary in that this is the largest joint technical venture and the largest operating piece of machinery that has ever been constructed in orbit. It is definitely not easy. It is not routine by any stretch of the imagination, even for operations that we have done many, many times. One of the things that we've learned in our history with the Space Shuttle and Space Station program is that we're always learning something new, even things that we've done many times before. You don't always know what you don't know. That being said, we have been able to take advantage of our experience with previous trust flights to gain some efficiencies in how we prepared for this flight. On some of the earlier trust flights, we had uniquely developed procedures that were unique for each particular configuration because the configurations were unique. This time we're able to make use of more generic procedures that we have documented, and that saved us on some procedure development time. and allowed us to focus a little bit more on refining our analysis for things like power capabilities and to give more attention to some of the payload operations that are going to be occurring. So just to summarize, I'd say that the things that we will benefit from by having done this before is that we do have a little bit more mental bandwidth, so to speak, to devote to payloads, doing payloads and other critical assembly operations above and beyond the installation of the truss on EVAs 2, 3, and 4. So I think that's going to be a real great benefit to the program. As far as when will we be over the hump, I won't start breathing easy until all of the mission objectives are complete and the shuttle crew is safely on the ground. However, given the issues that we had that we talked about before with respect to the previous solar array deployment, I'll be a very happy person once we've successfully deployed the S6 solar arrays and not had an issue.
All right, thank you again, Kwatsi and Paul.
Okay.
We have no further questions here at the Johnson Space Center, so with that, we'll wrap up this briefing. Coming up next on NASA television will be the NASA video file, and then we'll have our next STS-119 briefing at 11:30 a.m. Central Time. That will be the spacewalk overview, and then our STS-119 crew news conference coming up at 1 p.m. Thank you.